I will begin. Ahem. 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 Dear Father, we thank you for this day. Again, Lord, I thank you for the students, and the convocation's over, and just help us in this class just to glorify you what we do, Lord. In your name I pray. Amen. All right, so I want to explain to you a certain formula, and so that formula is the determinant today. Our goal today is to understand what is a determinant. Why talk about determinants? What do they do for you? And what's their motivation, all right? But also how to calculate them, at least the initial sum of that. So here's the first thing. The determinant, we want to say this, the determinant of two vectors, all right? It should be like the area of the parallelogram, which takes them as sides. So the parallelogram I have in mind here, it's got side A here, and then side A is also up here, right, that vector A. And then vector B goes here, and also here. It's a parallelogram. It's got the same vector for two different sides, right, just parallel translated. So if you stare at this diagram long enough, you can see that the formula for the area of this parallelogram is in fact A1B2 minus A2B1, all right? Let me try to explain to you how that works. Now this was a color picture when I scanned it. It doesn't seem to have come across here. I mean, I've scanned color stuff before. Oh well, I tried. Anyway, this is a little bit better than what's in the notes, which is like a tiny little picture, right? And let me just try to explain the mechanics of it to you. I'll post this in Blackboard so you can, if you want, print it out 3 times. Oh, actually just print it out once, and then you get scissors, cut it out. And what you can see, so let's just focus here. This big parallelogram, right? If you look at that and just compare it to the rectangle R1. So the rectangle R1 is this thing. It's got the R1 has one corner at the origin, the other one A1B2, right? So what's the area of R1? It's just A1B2, right? A1 times B1. We're going to assume that these are vectors with positive entries just to keep things uncomplicated. And so the area of rectangle R1 is A1B2. If you look at the parallelogram, there's a couple triangles that are found in the parallelogram which are not initially seen in the rectangle, right? So like, for example, T1, this rectangle up here, T1, if you look at that, you can move that down here. So T1 tilde is my notation for the moved T1. So like T1 tilde geometrically is the same as T1, and you just moved it down here. Now, here's the rub there, though. You notice that T1 has a little bit out here, which is actually not in the parallelogram, right? So by moving this T1 down here, I've, in some sense, added this area T3, right? So let's keep track of all the area we're going to get rid of up here. So I got to get rid of this T3 tilde area from the area of R1 to match up with the area of the parallelogram. So I move this down to here, but it's got the extra T3, so I'm going to remove it over here. On the other hand, I've also got T2. Well, T2, I could just shift over here to T2 tilde, right? And so by doing that, I've gotten all the area in the parallelogram, which is outside of R1, and I've shifted it inside R1, right? I've covered the whole rectangle R1 except for what? Except for R2 tilde. R2 tilde is exactly this box down here moved up there. This box down here has coordinates B1, A2. So what's its area? B1, A2. So what's the area of the parallelogram? It's A1, B2 minus A2, B1. And that's why we should define the determinant of a 2 by 2 matrix by the difference of the diagonal and the off diagonals. Because it gives me the area of a little parallelogram like this, right? You're like, well, but the determinant of a 2 by 2 matrix, so that's my definition for the sake of for here. Definition, determinant of A1, 1, A1, 2, A2, 1, A2, 2 is A1, 1, A2, 2 minus A1, 2, A2, 1. I mean, however you want to order that. So there's the definition of the determinant of a 2 by 2 matrix. Some simple examples. What's the determinant of the identity matrix? it's 1 times 1 minus 0 times 0, which is 1, right? What happens if I take the determinant of A, B, C, D transpose? That's the determinant of A, C, B, D, right? Which is AD minus CB, which, by the way, is also equal to the determinant of AB, CD. So at least the determinant of a 2 by 2 matrix, it can't tell, before and after transposition, same result, right? Another thing we might notice, if we take the determinant of, let's say, 1, 2, 0, 4, what do we get? We get 4 minus 0, right? Which is 4. What happens if we calculate the determinant of 0, 4, 1, 2? Yeah, we get 0 minus 4, right? So apparently switching the columns, right, gives us minus the same result. What's the significance of the sign here? What's the difference between the plus and the minus? If we draw a graph here, we can perhaps gain some insight as to what's going on. I mean, 1, 2, the vector 1, 2, what's it go? It goes over 1 up 2, right? So this is the 1, 2 vector, right? What is the, where's the 0, 4 vector? What's that look like? Something like this, right? So in contrast down here, I could maybe picture them using, so I got, 0, 0, 4 like this, and I've got 1, 2 like that. Right? So what's the difference? The 1, 1, 2 is here, 0, 4 is here. So if I measure the angle swept from like this to that, right? So the angle swept from the first vector, the first column, to the second column. Again, here, sweeping from the first column to the second column, right? What's the difference between these vectors geometrically? When it's positive, it means that we get to the second column from the first by doing a counterclockwise rotation, whereas we get a negative sign when it's a clockwise rotation to get from the first column to the second column. So that's the significance of the sign of the 2 by 2 determinant. It tells you whether the columns are related first to the second by a counterclockwise, that's positive, or a clockwise, that's negative rotation. There's another case, though, right? What if the vectors are the same? What if they're scalar multiples one of another? What if we had, the determinant of, say, vector v and then, say, scalar multiple v? What would that be? That's the determinant of, say, AB and then Ka, Kb. How's that work out? Akaba? No, akaba minus bk. Anyway, however you pronounce it, it's 0. So if the vectors don't actually fill out an honest-to-goodness parallelogram, the determinant's 0. These features that I'm showing you actually motivate the general definition. So one definition you could give for the determinant in fact, well, let me do a little bit more here. These things I should share with you. If I can find my notes, it looks like it. All right. So in Calculus 3, you guys study the cross product, right? And so this cross product, it's a vector which is perpendicular to the two vectors, right? And the length is related to the original one in a natural way. If you look at the triple product, the dot product with the cross product, we learn in Calculus 3 that this actually describes the volume of the parallelepiped with vectors A, B, C, and as edges. So this is the natural candidate for the determinant of a 3 by 3 matrix with columns A, B, and C. Right. Again, we want the determinant to describe signed volume. All right. Here's a picture. And make it bigger. So like if you have a parallelepiped with side A, side B, and side C, you can figure out the volume of that by doing some analytic geometry, and it works out to the triple product is the long story short. And so that's a natural candidate for the formula for the determinant of A, B, C, because that's the volume. Now what's the significance there? So I'm saying that the determinant of A, B, C is equal to actually plus or minus the volume of the parallelepiped. Now this parallelepiped I can define for you a little bit more specifically. It's the set of U1A plus U2B plus U3C such that U1, U2, and U3, these are positive constants, all right? And they sum at most to, oh, that's it. So they sum to 1 at most, basically. This is also called the convex hull. When you go on and study deeper linear algebra, you learn this thing called convex linear combinations. They're linear combinations where the coefficients aren't free just to be anything. They're limited to range between 0 and 1, like this. But anyway, the parallelepiped is the convex hull of the vectors A, B, and C for what it's worth, and so the definition is that the determinant of A, B, C should be plus or minus the volume. Now, let me just tell you what the plus or minus means. So if we have this vector, if A looks like this, and B looks like this, all right, then the cross product of A and B we learn in Calculus 3, we use right-hand rule A cross B. So like the cross product of A and B is where? Using the right-hand rule. In my picture, A cross B would be what? Something like this, right? By the right-hand rule. So this basically defines what is up for the plane with tangent vectors A and B. All right? So the triple product. When you look at the determinant of A, B, C, it's going to be positive, and it's actually going to describe the volume of this parallelepiped if C is where? So like if C looked like this, for example, let me call that C1, then the determinant of A, B, C1 would actually be equal to the volume of P, right? On the other hand, if C2, if this vector is actually below the plane, then the determinant of A, B, and C2 will actually be minus the volume of the parallel pipe bed. Another way of saying this is you can define a set of 3 vectors to be a right-handed triple if the determinant of A, B, C is positive. Definition: A, B, C is right-handed triple if the determinant of A, B, C is greater than 0. If the determinant of A, B, C is negative, that means it's a left-handed triple. Now, sometimes people also assume that A and B and C are perpendicular, but let me not assume that for our purposes at the moment. Okay? So this motivates the determinant. The determinant is volume. It's, well, signed volume. That's the point of the determinant, is to calculate volume. But it does something else along the way, you see, because what would happen if A, B, and C are coplanar? What should the determinant of coplanar ABC be? What's the volume spanned by three vectors which lie in the same plane? Yeah, the volume 0. So that, and what happens if all 3 vectors are collinear? What's the volume of that parallel pipe bed? Well, it's also 0, right? So the determinant of ABC being 0 detects linear dependence amongst A, B, and C. It detects whether or not A, B, and C are actually in genuinely different directions, or if in fact they are lying along the same line or the same plane. That's pretty nice, right? I mean, because that means if you have as many vectors as the size of your vectors, you can just shove them in a determinant, calculate the determinant. If the determinant's positive, excuse me, if the determinant's non-zero, that shows you that the vectors are linearly independent, is one of the things we're going to prove. So, yeah. But our immediate application, our motivating application, is that determinant is volume. And when I say volume, I mean the generalization of volume. All right? I mean, if I have 4 four-dimensional vectors, I can still talk about the volume of those in the sense, the 4-dimensional sense. All right, well, let me give you the motivations aside. Let us write the general definition for you and do some calculations. Put this away here. I think, yeah, I'm going to put it away. It's okay, I got to reset the Zoom, otherwise I'll be unhappy. Yeah, we're good. There you go. So, definition, guys. If A is an n by n matrix, so it's got to be a square matrix over field, all right? Okay, that's not true. I mean, you could take entries from a ring. We could define the determinant over a commutative ring, but I'm just going to assume it's a field for the sake of, applications in here. We define determinant, which is going to be a mapping from Fn by n to F via the following formula. The determinant of A is equal to the sum I1, I2, In equals 1 to n of the Levi-Civita symbol, epsilon, I1, I2, In. AI11, AI22, AINN, where epsilon 1, 2, n is equal to 1, and all other values are obtained by complete antisymmetry of epsilon I1, I2, In. let me unravel this notation for you in the 2 by 2 case. All right, let's start out small. So I'm saying epsilon 1, 2 is equal to 1, all right? Antisymmetry says epsilon 2, 1 is equal to minus epsilon 1, 2. But that's equal to minus 1, right? What did we learn about the diagonal of an antisymmetric matrix? Remember? It's 0, right? So if we have antisymmetry in a pair of indices, it forces those components to be 0. So by definition, epsilon 1, 1 and epsilon 1, 2, epsilon 2, 2 are both 0. And generally speaking, this epsilon symbol is only non-zero if it has distinct indices. It forces a selection of n distinct indices. It forces every term in the determinant to involve all different choices for I1 through In, taken from 1 to n. Anyway, so the determinant of A11, A12, A21, A22 is just equal to epsilon 1, 2, what we got? A11, A22, plus epsilon 2, 1, following the pattern up here, guys, 2, 1, A 1, 2. Just to be clear, this 2 and that 2 are linked. This 1 and that 1 are linked. Over here, this 1 and that 1 are linked, and this 2 and that 2 are linked. Right, that's the pattern. Right? But of course, what is that? That's exactly the 2 by 2 determinant formula that I motivated from the area of a parallelogram that started today, right? To further unravel this pattern, let me talk about n equals to 3. Here we have epsilon 1, 2, 3 equals to 1 by definition. So epsilon 2, 1, 3 is equal to minus 1. So epsilon 2, 3, 1 is equal to 1. So epsilon 3, 2, 1 is equal to minus 1. So epsilon 3, 1, 2 is equal to 1. So epsilon 1, 3, 2 is equal to minus 1. I think I've got everything now. There should be 6 distinct triples here. And it's fairly easy to see how the pluses are related, right? If you look at the plus, plus, and plus, see what we got? You've got 1, 2, 3, or push the 3 back to the start, 3, 1, 2, or push the 2 over the edge, and you get 2, 3, 2, 3, 1. So those are cyclic permutations of 1, 2, 3. And then the other 3 are the so-called anti-cyclic permutations of 1, 2, 3, namely 3, 2, 1, 2, 1, 3, and 1, 3, 2. You're counting down in these as you go across, with the understanding that going from 1 to 3 is counting down in the sense of looping. Yeah. Anyway, that's what it works out to. And so the determinant of a 3 by 3 matrix is, what is it? It is epsilon 1, 2, 3. Excuse me. Let's see here. So we're always doing. Let me fill in the gap 1. A fill in the gap 2. A fill in the gap 3. Plus epsilon A fill in the gap 1. A fill in the gap 2. A fill in the gap 3. Plus epsilon A fill in the gap 1. A fill in the gap 2. A fill in the gap 3. I'm getting tired of this. Dot, 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 dot. Plus epsilon A fill in the gap 1, A fill in the gap 2, A fill in the gap 3. You notice that the second index here is fixed in this formula, right? So going through the, so 1, 2, so this 1, 2, 3, right? This 1, 2, 3 goes here. And then which one do you guys want to do next? I mean, we can do, I'll just go down this list, 2, 1, 3, yeah? So that's 2, 1, 3. And then we've got what? Epsilon 2, 3, 1, 2, 3, 1, and so forth. Tell you what, I'll end with the last one, 1, 3, 2, and 1, 3, 2. Yeah. So anyway, there's 6 terms here, right? 3 pluses, 3 minuses. Kind of a drag, right? A little bit. So thankfully, there is another way to calculate these determinants that I should point out for you guys. And that is the so-called Laplace expansion by minors. Now, there are some properties of the determinant we could point out before we go even any further than this. What can you tell me about the determinant? What would happen, for example, if I put in the identity matrix? If I look at the determinant of I, how would that work out? So we'd have, the sum over all those indices, epsilon, I1, I2, in. And what are the components of the identity matrix? We'd have delta, I11, delta, I22, delta, INN. What's that do? Well, that collapses the sum to just what? Epsilon, I1 replaces with 1, I2 replaces with 2, n. Collapsing those sums, so we calculate directly from the definition that the determinant of the identity matrix is not 0. This, by definition, is 1. In other words, we're saying that if you took a hypercube, which has the unit vectors in the Cartesian coordinate sense of length 1 all around, the volume of that n hypercube is 1 by definition. This essentially sets the scale factor for volume. So the determinant of the identity matrix is 1 anyway. So that's one thing we could say. Another thing you could say is that this mapping is like linear in each column. If I took a particular column and I replaced it with a linear combination of that, if I replaced one column with like a linear combination of columns, for example, if I had the determinant of A, plus like a matrix which is the same as A, except for the, like the kth column where I have a BK times C, then I could prove that this is equal to the determinant of A plus C times the determinant of the mostly A matrix with the BK column there. So I have some sort of like linearity column by column. If you look at the formula, if I replace one of those columns with a linear combination of things, I can break it up into 2 big sums and get 2 determinants. So I can see that from the definition. But this, even for a 3x3 case, gets pretty old pretty fast. And so it's nice to know there's another way to calculate the determinant, and that's Laplace's expansion by minors, which I will not prove in here. There is a proof in my notes, and it is horrible. I mean, this is a technical result. All right, this is nasty. Nasty business. Now, here it is, though. So the determinant of, let's say, A, B, C, D, E, F, G, H, I, all right? I'll show you Laplace's expansion by minors across the top column. So it's A times the determinant of E, F, H, I minus B times the determinant of D, F, G, I, all right, plus C times the determinant of D, E, G, H. But you know how to do the determinant of 2 by 2s, right? So like we can finish this here. This is really A times EI minus HF minus B times DI minus FG plus C times DH minus EG, which if you look at it is AEI plus BFG plus CDH minus AHF minus BDI minus CEG. Like I said, 3 pluses, 3 minuses, and you can even see the pattern if you look at it. Let me show you. There's a kind of cute trick for doing the 3 by 3 case, which I don't know how to tech, so it's important I do this on the board. So if you do A, B, C, D, E, F, G, H, I. All right, then I write it again. A, B, C, D, E. I don't think you need to write all of it, but I'll write it all. G, H, I. And you write it neatly. Then you can see the pluses from just multiplying like so. See this AEI is this term, right? I gotta get my colors. Got my green, orange. Get my purple out. This is a chance for all the colors to come out and play. Ooh, turquoise. We could use that much. Let's see here. So you got your dark green. I don't want that. Sorry, I'll try to go on here. BFG, of course, big friendly giant. There we go. Sorry, stupid kids. CDH, poisoning my mind. CDH is right there, and then the other ones, the minus, the huff. A huff is like this, right? See that? And come on, I gotta have a blue here. Oh, purple. Let's see here, BDI, like that. Hey, this is pretty cool. I did not plan on those coming out in the same order as in the picture. That is an accident. They could have gotten intertwangled. There it is. So this is the 3 by 3 crossing trick. I will tell you right now, this does not work for 4 by 4 matrices. Do not try to do it for 4 by 4 matrices. You would be wrong. So how do you, but it's nice enough, right? So if we've got the determinant of, say, 1, 2, 3, 4, 6, 6, and then 5, 8, 9, that is clearly 0. I know this because I created row 3 by adding rows 1 and 2. So the set of rows is linearly dependent. I also know that the determinant is constructed, and this is also non-obvious. This is very non-obvious. But this is the determinant of A transpose as well. The general determinant also has this property, which I will not prove. There's a sketch of the proof in the notes. But the determinant is invariant under transposition as well. Now, so I know this is going to work out to 0. what do you guys want to do? You want to do the crossing trick, or do you want to do expansion by minors? Tell you what I'm going to do. I'm going to do an expansion by minors on the middle column. Check this out. So that's 2 times the determinant of everything that's not here. So what's not in the 2 middle column? The 4, the 6, the 5, the 9. And I just made a mistake because for the expansion by minors, you got to keep in mind this set of signs. Plus, minus, plus, minus, plus, minus, plus, minus, plus. So that 2 is in the minus spot. So the expansion by minors puts a minus here. Then I do plus, starting to debate whether I should have put this table somewhere else, 6 times the determinant of everything. So you look at the 6, which is here, and you basically cross out like that and take whatever's left over, which is 1359. All right? And then we do plus 8. Aha. Plus 8, take that table, times the determinant of everything that's not in that row and column. So that leaves me 1436, or 1346 as I usually read it. Minus, plus, oh yes, thank you, minus. Very good. And so whatever that it works out to, you got minus 2 times 36 minus 30 plus 6 times 9 minus 15 minus 8 times 6 minus 12, which is 0. I know in my heart it's 0. I haven't done the arithmetic, yes? Oh, I gotcha. Yes, you're right. Thank you. Had I put it into a computer algebra system, I would have been told mismatched delimiter or some such thing. So, or I don't know. I would have maybe, I don't know what I've been told, but I do appreciate the correction. Okay, so 4 by 4. 4 by 4 case. I'm going to show you an example rather than writing out a symbolic one. Suppose I had the determinant of 1, 2, 0, 3, 4, 6, 0, 7, 1, 1, pi, 2, and then 0, I don't know, 0, 0, 3. Thank you. So I got stuck there. Now there are 2 kind of natural candidates to try here. We can either do we can either expand on the 3rd column or the 4th row. That would be the smart thing. What do you guys want to do? Expand on the 3rd column? Let's expand on the 4th row since we haven't done that yet. Something like that yet. So let's do the Laplace expansion by minors across this. Again, the rules are plus, minus, plus, minus, plus, excuse me, minus, plus, minus, plus, plus, minus, plus, minus, minus, plus, minus, plus. So plus 3, and then we do the determinant of everything else. So 1, 2, 0, 4, 6, 0, 1, 1 pi. And then, of course, we also, I mean, to be fair, you also have minus 0 times the determinant of 2, 0, 3, 6, 0. So everything I'm writing is not needed to write down because these things, you know, are 0. 1, 4, 1, 0, 0 pi, 2, 3, 7, 2. minus 0 times determinant 1, 4, 1, 2, 6, 1. I'm reading columns. 3, 7, 2. But I didn't even, I mean, do I need to write any of this? All 0. And that's why we chose the fourth row to expand, because that simplifies the calculation, right? Which is nice. So I'm supposed to calculate this. So I got 3. And then, oh, I think the smart thing here would be to expand on what? That one, right? So that's going to be 3 times pi. Wait a minute. Plus, minus, yeah, plus, times the determinant of 1, 2, 4, 6, which is 3 times pi times 6 minus 8. So the answer is minus 12 pi. Oh, I'm sorry. Did I say minus? I meant minus 12 pi over 2. No, sorry. Yeah, no. You're right. You guys got me. You guys got me. Thank you. Much appreciated. So what would that mean? So let me tell you the theorems, all right? I probably won't have time to prove any of these today, really. All right? But I think it's important, probably important for us to state a few theorems. So this is just a method to calculate determinants, right? Which is technical and ugly to prove. But, there it is. But a nice theorem, perhaps the number one theorem, is that A inverse exists if and only if what? Yeah, the determinant of A is not equal to 0. That actually is really easy to prove if you know number 2, which is probably the most important and most non-trivial property of the determinant is the following. The determinant of AB is equal to the determinant of A times the determinant of B. That little identity, that the determinant of the product is the product of the determinants, is not an easy thing to prove. But once you have it, all kinds of results fall out. So those are big ones. 3, if we have S, V1, V2, Vn, subset, of Fn, then S linearly independent if and only if what? If the determinant of the matrix of S is not equal to 0, right? So this gives us a really nice check if we happen to have the same number of vectors as the dimension we're asking the question in. I have a homework problem in mission 3 which explores how to ask similar questions if you, say, have 2 vectors in 3 dimensions. How would you check linear independence of those by looking at 2 by 2 determinants of subsets of their components or something like that? It's kind of complicated. If you have less than n vectors, in n dimensions, like if I had, n minus 1 vectors in n dimensions to check linear independence using determinants, we have to look at not just one n minus 1 determinant, but like a whole bunch of them to gain information. So it's most useful when you have as many vectors as the dimension in terms of studying independence directly. So these are the big ones. There are further calculational properties for example, the determinant of a block diagonal matrix. So if I have a block diagonal matrix like this, one other thing I'll share with you, which probably, that's all folks, probably be useful for you, is that that is also the determinant of A times the determinant of B. So like the determinant of a block diagonal matrix is the product of the determinants of the blocks. This is very helpful if I ask a homework question which is about this. What else can I tell you? I've already told you the determinant of the transpose is the determinant of the matrix, determinant of I. What else can we say? Oh, here's one that gets students. What happens if you calculate the determinant of a constant times a matrix? How does that work out? What's that? C to the n times the determinant of A, spoken like a student who has extensive experience with matrix calculation. Very good. When I tested math major seniors in Math 450 on this inadvertently in a quiz last semester, I found out that there's a fair number of people who somehow managed to get past 321 and not learn that. Yeah. So it's not linear in the sense like you pull out the power. If you look at that, for example, if you look at the determinant of the matrix 2, 2, 2, it's easy enough to understand why that is. Right? Yep. Yeah, here we're talking about an n by n matrix. Yep. Thank you. I mean, for example, the 3 by 3 case, it's easy enough to see for the diagonal that this would be 2 times 2 times 2, right, which is 2 cubed. To give you an example of that, pulling the 2 out as a cube, because that's 2 times I. All right, well, let's do one proof. Suppose let's prove that 2 implies 1 actually. So suppose we know that the determinant of A, B is the determinant of A, determinant of B. In fact, we're going to assume that. I have a proof in the notes, but I probably won't go through it in here with you guys. It's rather technical, and it doesn't really lead to anything else. So we're just going to assume that this property we know, which is a rather technical property, is known. Determinant of product of determinants. If A inverse exists, right, then what? We know that A inverse is equal to I, right? Hence what? The determinant of A inverse is what? The determinant of A times the determinant of A inverse, right? And that's equal to what? Yeah, it's equal to 1 because the determinant of I is just 1. Thus what? Thus the determinant of A is not equal to 0, right? That's just basic field multiplication stuff. If you got the product of two numbers in a field is equal to 1, you can't have one of them as 0, right? Now, the proof in the other direction, it is an if and only if proof, but the proof in the other direction requires a little bit more thought. I'll try to explain that more next class. So, thanks, guys.